Today we're talking about section 11.6, finding the areas of regular polygons, whether it's a regular hexagon or a regular octagon or a nonagon or something like that. It is also the last section we'll be covering this year. That's an exciting thing. If you take a look at the figure on the right, here I have a regular hexagon, and it's inscribed inside of a circle. So you can see that we have these radii, which is plural for radius, going from the center of the circle, which is also the center of our polygon, to the edge of the circle, which happens to be the vertices of a polygon. So for a regular polygon, we do have radii, and they go from the center of the polygon to the vertex, or the different vertices here. So this is considered a radius, and this is considered a radius. It has to go from the center to the vertex. If it doesn't go from the center to the vertex, let's say it goes from the center to a side. And if we're measuring distance from the center to the side, it should be a perpendicular distance. So that's called an apothem. An apothem is a segment that is the distance from the center of the polygon, to a side. So that's an apothem. So radius goes from the center to a vertex, where the apothem goes from the center to the side. And these are some important vocabulary words that will come up in a bit so we can find these areas. We just have to kind of introduce this first. Also, we have to talk about central angles. A central angle is an angle formed by two radii. So center to vertex, center to vertex, and it has this whole section in here. So a central angle is an angle formed by two radii. And we've seen those before. We call this an arc measure when we talked about arcs and circumference and sectors and area. This was called an arc measure. But since we're talking about regular polygons, not circles, we can't call it an arc measure, but we have to call it a central angle. And so we're going to use these things to find the area, but first let's do some practice with these new vocabulary words. For example 1, we're going to find these angle measures in a regular polygon. So in the diagram, ABCDE is a regular pentagon inscribed in circle F. This symbol here does refer to a circle. Find each angle measure. First of all, the measure of angle AFB, so AFB. Well, AFB is a central angle. It's a central angle because it's formed by two radii, center to vertex, center to vertex. So we're looking for this measure here. Now, we have plenty of central angles. We have this purple one, we have an orange one here, a green one I'll draw here, blue one, red one. So you can see in this pentagon we have 5 central angles. That's no coincidence. You have a 5-sided figure, you will have 5 central angles. And all of these 5 central angles that are congruent, because this is regular, form this circle, which is 360 degrees. So all your central angles add to 360. And since there's 5 of them, take 360 and divide it by 5. That's the measure of one central angle, which here is 72 degrees. So the measure of angle AFB is 72 degrees. Again, because these 5 central angles are congruent, and they all add to 360 since they form a circle. Let me erase this though so we can more clearly see the picture in the problem. So since AFB is a central angle, here it is 72 degrees. For the second problem, find the measure of angle AFG. AFG. So it's this half of it. Well, let's not make an assumption that it's exactly half of 72. Let's kind of prove it. So, since these are both radii, they're both congruent, which makes this an isosceles triangle here. Well, an isosceles triangle, this altitude is also an angle bisector. And that's back from chapter 5. So these halves are going to be congruent. They are both 36 to make the whole thing 72. So for part B, that half, the measure of angle AFG, is 36 degrees. And lastly, we want to find the measure of angle GAF. I don't know why I wrote that. So GAF, I'm sorry. Let me fix that a little bit. It's kind of messy. GAF, which is this angle down here. Well, in this little triangle, we know that this angle we said was 36, this is 90, and they should all add to 180. So 36 plus 90 plus what should give us 180? That what is 54 degrees. So if you add 90 and 36 and subtract it from 180, you end up with 54. Let's do one more quick example here. We're going to skip the second one and just focus on the first one. Identify the center, or radius, an apothem, and a central angle. Let's start here with the center. The center of this square inscribed in this circle is P. The center of the circle and the center of our square. If we're going to look for a radius, it goes from the center to a vertex. So you could say px or xp. You could also say py or yp. Those are both going from the center to a vertex. An apothem, again, goes from the center to the side, measuring that distance perpendicularly. So PQ or QP is our apothem. And lastly, we're looking for a central angle. Well, the central angle is this entire angle here formed by two radii. So XPY or YPX. Is our central angle. Now let's move on to how we can actually use these different things to find the area of a regular polygon. And I'm going to prove the formula to you before you look at the formula so that you know where it comes from, how it works. Usually in math, all formulas we use are theorems of some sort that have been proven. So I'm going to prove this to you. Let's say we have an area of any regular n-gon. I should note that they are regular. So we know that from our first initial example, you can divide it into several triangles. These central angles form different triangles here. So here we have 3 triangles. If we can find the area of each triangle and then just add them together, there's the area of our polygon. And all these areas or all these triangles are congruent because it's a regular polygon. So all we have to do is find the angles of the triangles and add them all together. So to find the area of this one triangle, it's 1/2 times the base times the height. But in this case, our base is S and our height is A. So 1/2 times A times S. That's one triangle. Well, we don't just have one triangle, we have many triangles. So in this picture, we have 3, and we probably continue going around here. So how many triangles do we have? Well, we have 1 for each side. Because remember where we started, if you have if you have a hexagon, you have 6 central angles. If you have a pentagon, you have 5 central angles or 5 triangles. So the number of sides is the same as the number of triangles. So I'm going to call n the number of sides, which is also the number of triangles. So we know that the area of this regular shape is all of these triangles times the number of triangles. So 1/2 times the apothem times the side times the number of sides. Well, if I were to kind of, using the associative property, divide some of this into parentheses, if I have the number of sides times the length of a side, that's really the perimeter. If I have 6 sides and they're each 8 centimeters, I just do 6 times 8 and that's my perimeter. So I'm going to call this the perimeter instead. So the area is really 1/2 times the apothem times the perimeter. And that is our formula. 1/2 times the apothem times the perimeter. And again, this is the theorem, which I just showed you a very informal proof of. And this is the one we will primarily look at. You can also, instead of perimeter, think of the number of sides times the side length, but it's easier to just think of perimeter. So if you want to pause it and take some notes with this, that's fine. Otherwise, I'm going to move on and do a couple examples to finish off this video. Let's do 2 of them. Let's start with the simpler one first, unlike in class. So let's make some room here. So find the perimeter and the area of a regular polygon. This is a regular pentagon. So we know that the perimeter is just all the sides added together. We don't know what the sides are. What we do have here is a right triangle. So we can solve for this variable x using our Pythagorean theorem. 8 squared equals 6.5 squared plus x squared. And so using our Pythagorean theorem and subtracting from both sides and taking the square root and everything like that, let me go ahead and punch this in here. Square root is there. We end up with x as being about 4.66. I'll leave it as nearest hundredth. So that's x. That's not the length of a side. That's only half the side. The whole side is here. So that means the whole side length is 4.66 times 2, which is about 9.32. And since we know the side length, we can find the perimeter. Perimeter equals the side length times the number of sides. So perimeter is the side length times 5 because this is a pentagon. So the perimeter here is 9.32 times 5, which is 46.6. And this case is just units. Now to find my area, the area of this guy should be 1/2 times the apothem times the perimeter. It's lowercase a, so that's apothem. Well, we're given the apothem is 6.5 because it's from the center to the side and it's perpendicular. And we know the perimeter now is 46.6 units. So if we multiply 6.5 times 46.6 times 1/2, our area is 151.45 square units. There we go. Find the perimeter. We knew the apothem. Yada, yada, yada. There is our area. Let's try one where maybe we don't have an apothem, or we don't have a radius, or we don't have something that we need. Here we have a regular nonagon, which is 9 sides, inscribed in a circle with a radius of 4 units. Find the perimeter and the area. So here we have a radius. We know there's 9 sides. We don't, however, know the apothem. And the first thing we need to do is find our perimeter, but we don't know the side length. I'm going to draw this triangle a bit larger out here. Now, we can't use Pythagorean theorem in one of these right triangles because we only know one side. Right now, we don't know if it's a 30, 60, 90 or a 45, 45, 90. We don't have an angle to use trig, but we can find an angle. This is a nonagon with 9 sides. And all of these central angles should add to 360. And there's 9 of them since it's a nonagon. So we can take 360 and divide it by 9 and find out that it's going to be 40 degrees for this central angle. So that whole thing is 40 degrees. That means each half is 20. And now we can use trig to find for this length, so we can solve for s, so we can solve for our perimeter. So using trig, we can use the opposite, call that x, over the hypotenuse, so we're using sine. So the sine of 20 equals x over 4. And if we cross multiply using the sine of 20, we'll end up multiplying that times 4. We end up with x being 1.37. And since there's 2 x's, we can find the whole length by multiplying that times 2. So 1.37 times 2. So 2.74 is our total side length. That means we are ready to find our perimeter. The perimeter is the side length, which is 2.74, times the number of sides, which is 9, since this is a nonagon. So our perimeter here is 2.74 times 9, which is about 24.66 units. So we couldn't just use Pythagorean theorem like in the last example. Here we had to use some trig. Let's also use something else to find our apothem so we can find our area. Well, our apothem is here, so we have 2 options. One, we could use cosine and call this a. And we can say that the cosine of 20 is a over 4. And then you could use cosine. And if I do that, I'm taking the cosine of 20 times 4. and my apothem ends up being about 3.76, and I can use that in my perimeter to find my area. You also could use Pythagorean theorem here, since you know that this is about 1.37 and that's 4. You could use Pythagorean theorem to find that as well. That's not a problem. So the area is 1/2 times our apothem, which is 3.76, times the perimeter, 24.66. And if we multiply all that stuff together, give me one moment here, we end up with an area of 46.36 about, and that's in units squared. So sometimes you can use Pythagorean theorem, sometimes you have to use trig. It depends on what you start out with and what you need to find. Hope this video is helpful. Send me an email or see me before or after school if you need some extra help.